for Sexual Reproductive Health and Rights in Uganda, promote maternal and child health. The Institute also supports a capacity building to strengthen adolescent and young people-friendly services in southwest Uganda. The Institute of Tropical Forest Conservation, which is a leading Ugandan research institution working primarily for biodiversity conservation and the sustainable management of natural resources in the Albertine Rift ecoregion. The university is led by a diverse management team under the stewardship of the Vice-Chancellor, Professor Celestino Oboa, who have steered the university towards its vision of becoming a center for academic and professional excellence in science and technology. The university pursues its vision through focus on research, innovation, and community engagement. The university is on a mission to provide a quality and relevant education with a key focus on application of academic knowledge to community development. In pursuit of her mission, MAST established the Faculty of Interdisciplinary Studies, which offers uniquely tailored courses to equip all our students with the important social sciences knowledge to be able to respond to the needs of society. The pioneering community-based education, research and service, student community training and internships gives our students an opportunity to work like environments before graduation, but also exposes them to the challenges of the communities and affords them an opportunity to use their training to address the challenges. Our Center for Innovations and Technology Transfer is an important vehicle through which research within the university trickles down to industry and community. The center houses the Consortium for Affordable Medical Technologies, CAMTech, which focuses on developing affordable medical technologies to address health challenges of the community. Farm Biotechnology and Traditional Medicine Center, Mbarara World Bank Project, which carries out research and development of traditional and herbal medicines and remedies. Business Incubation Clinic, which offers mentorship and seed funding to entrepreneurs. Soft Incubation and Innovations Unit, which carries out software development and mentorship of developers. The center runs innovative short courses that feed the production cycle. Our campuses are designed to offer an accommodative and inclusive education. In MAST, everyone matters. The services rendered produce an all-round graduate, one with the necessary skills to transform lives and have a positive impact on communities and the world. MAST has attracted students from all over the world. This is due to the homely environment, highly qualified faculty, and the outstanding global network of nearly 20,000 alumni who have positively transformed the communities they serve. This is Mbarara University of Science and Technology, where success is not an option, but a must. Succeed, we must.
Thank you so much, ladies and gentlemen. That's Mbarara University of Science and Technology, where you are. Amidst us, ladies and gentlemen, we do have the University Secretary, Mr. Biaruhanga Melkwaya. Thanks you for joining us. We have the Dean Faculty of Applied Sciences and Technology, where we are right now, Dr. John Zobongoloch. This is the youngest faculty in Mbarara University, but it's the most well-fed, growing so big, with big numbers, with big donors, and big partners like you. Ladies and gentlemen, with us also we have guests from Makerere, and in no specific order, in absentia we recognize the presence of Engineer Dr. John Baptist Chirabira. I think he's online. You can clap, he's hearing us. We do have Engineer Ronald Kaima. Yes, thank you for joining us. We do have Engineer Vianney Andriga. And we have Engineer Kenneth Sekatawa. Thank you. And we do have Engineer Florence Nantaba. Thank you for joining us. We do have Mr. Moses Chigozi. Yes, Mr. Chigozi. Oh, that one is supposed to be my uncle, Wefumbe, yes? So we do also have students with us from Makerere. Please just wave to us for recognition so that it's a meet and greet. Thank you. And then we have Mbarara University faculty. Please also wave to our people. Yes, thank you for joining us here. Mr. US, without wasting any other time, why we're here is to enhance the engineering business, literally, in Uganda. And these people have taken it far to collaborate with so many others. The purpose is to see how best to bridge academia and industry. And each country has its own goal. Uganda is working with Petroleum Authority of Uganda and Makerere University to see how best to improve oil recovery. And these ones have moved a step ahead. And the team lead in Mbarara University is Engineer Sagala, who is right here. And I will be glad to know the team lead from Makerere. And we have a representative from Petroleum Authority of Uganda, Mr. US and Mr. Dean. With you here, we're also having people online from Namibia. We're having different professors there that will give us a presentation. But in Namibia, the study we're having with them, they're interested in using to develop fertilizers to help in agro and horticulture business. This has gone as far as South Africa. In Nigeria, they're using it for face masks that can absorb toxic gases that can be used by the military, and the case study is being used by the military. In the UK, the Imperial College of London, these are using it for carbon capture and storage. I cannot speak more language in engineering, but rather invite Engineer Sagala to give us an overview about this. Thank you so much. You're free to use the podium. I didn't use it for height issues.
Okay. Thanks, everyone. My name is Dr. Farad Sagala. Actually, my name is supposed to be Fahad, but the enable issues in Uganda made it Farad, and I'm comfortable with it. So if you find the name Fahad somewhere or Farad, I'm okay with the end of them. So I welcome all of you to Mbarara University in Uganda. As I said, my name is Dr. Farad Sagala. I have a PhD in petroleum engineering, which I got from the University of Calgary. And the idea of research, if you finish a PhD, it becomes part of you. And if you don't do research, you cease to, breathe. So when I came to Mbarara University in 2021, 3 years back, immediately I started initiating my research activities, and many have been ongoing. And recently now we have this one. The first one we were working with was from the Tuasa. This is from Italy. It was mostly for equipping the lab, and they gave us some equipments which we are yet to initialize with our students who are going to stay here for internship. They may use them for the internship activities. These were the support we got from the TWAS, which was our project, which we got initially. Then we have other numerous DGRT projects that have been keeping us ongoing, both with the faculty staff at first. We have some few projects we have been doing with the individual staff members. And then this one for the Royal Academy, I can say it has been somehow a bigger one compared to the previous ones because of the collaborations it has brought to us. First of all, the people who are supporting us to do this research, they are from the Royal Academy of Engineering. Royal Academy has a lot of support for Sub-Saharan Africa, which I will be happy to share with the faculty staff here to explore as much as you can. Recently, we had a workshop in South Africa, and I realized that there are many people who are maximally using their resources and they are benefiting, especially Nigeria and Kenya. Actually, last year, Nigeria was told not to apply because for them they maximize and they have, out of the 30 applications, 20 are Nigerians. We were only 2 Ugandans there, and possibly because people are not aware. And this grant is straightforward. Let me say like this. If you have your proposal well aligned, and they have very many segments which I will disclose to you. So in this project, the HEPSA one, in our section, we are doing joint research, which is one of the segments, which is part of the HEPSA. They have another one which they also do with the institution of engineers in every country, and still with some universities. So I found people from Tanzania, Kenya, Malawi, they all have these different segments of HEPSA. I found even some people who have been with HEPSA for 8 years. So for them, as long as you deliver, you can keep on renewing as much as you can. The only thing, just keep on having deliverables to their expectation. So what we are doing for us, the HEPSA, the theme, we want to bridge a gap between academia and the industry. So the major core for this project, you had to find a partner in the industry. So in Uganda, and you had to have a minimum of 5, they call them spoke universities. If I tell you something very interesting, I wrote this proposal in 2 weeks, only 2 weeks. And I had to find a partner in UK, a partner in any African country. So I thank Professor Chirabira, who is not here with us. He's in India, he has some issues, and he has been so supportive. I appreciate him a lot, and he's still supportive. So I reached out to Professor Chirabira, who is working on Mapro Nano. They are having a lot of research on nanotechnology in Uganda, and I introduced the idea to him. For him, he's always open to any support you introduce to him. Is always a free man and always very helpful. So I told him, Prof, this is the thing, we need to develop this proposal, and we have 2 weeks. And he said, we can make it. So I gave him the draft. Within 2 days, he gave me the feedback, and I had to reach out to look all those spoke partners which we are mentioning here. One of them is in Imperial College. So this team for Imperial College and others, they are in Kampala. They are following us right now, but they are coming tomorrow because they are waiting for our colleague, Professor Anne from Imperial College, to join them. Then they come here, and tomorrow we are going to be with them. So tomorrow possibly we are going to play this video again so that they can have a glance of what we have been doing, and possibly I will give another recap. So I had to find that professor from Imperial College, Professor Anne. She was a very interesting lady. She was born in Uganda. Her parents were working in Mengo Hospital. And when I was looking for my PhD, one of the colleges which had given me admission was Imperial College. Then she was going to be my supervisor. That's how we got the in between. So when I sent her a notification that I want you to be our spoke, she was straight away open and very supportive. Then I had to reach out to other countries. The one from Nigeria, we got him. We had here the AWB. I think Vincent, you remember that. So this partner, I got him from that project. Then the one from Namibia, I also got him somehow through collaborations. So one is from Namibia, one from Nigeria, and then Imperial College. Then the industrial partners, the HEPSA wants you to develop something and then apply. Because even they have another category where you pitch your business idea, which is in form of technology, and they see if there is any way they can commercialize it. So this is so active in UK. If you follow their page on LinkedIn, you can see the pitches from business ideas, which are different, and people are trying to win support from the Royal Academy. So all the professors here in your free time, check out the Royal Academy. It has a lot of support for us. We just need to see where we can tap these opportunities. So the material we are developing, since we are doing joint research, we need application. So the application which we proposed, since I have been outside for some time, I'm just now transferring the knowledge. Most of the technology we are now proposing, I have tested it and I know it's working. So we are not in the testing stage. There is one company, you can check on it on your, if you have some time, it's called the Carbon Oxtec. It's in Calgary. For them, they are developing fertilizers from oil waste, which we call it petroleum coke. So they develop some fertilizers which they try to integrate with some additives depending on the application. So these are the first people who initiated the formulation of Bio-Silica, which we get from rice husks. So when they got their first sample for the rice husk, it came from Mexico. And when we extracted the first batch of Bio-Silica and we applied it for our fertilizer application, it gave us positive results. But the interesting part with nanomaterials, depending on the application, we can always play with the surface. So all those applications you have had, we can use the same material, but we play with the chemistry. So what we had to do here in Uganda, find some students, we introduced to them some of these ideas, and some of them have embarked on their master's degree. We are supporting them with both the tuition and the experimental plan is underway to make sure that they can complete their master thesis working on this same project. So in Uganda, we are working with the Petroleum Authority. Our colleague is coming, so they sent us one manager, I think, for operation from Petroleum Authority. We are working on how we can use these nanomaterials to enhance oil recovery. So enhancing oil recovery has been my research interest for a while. And there are very many technologies which we can use. And nanomaterials is one of the avenues that we can apply to maximize productivity at a very low cost. So when I was doing my PhD, I had to publish over 5 papers on only nanomaterial application in enhancing oil recovery. So we had to introduce this same idea to our students here. So I have right now 4 master students. They are registered in chemistry. They are all working on Bio-Silica for different applications. So then for Namibia, we are working with that company in Calgary, the Oxtec, to develop their fertilizer. And in fact, we are trying to have one first batch of the sample for them to test. Then for Nigeria, it's for the face mask, as we said earlier. And then for UK, it is of interest that for them, they are not doing too much research in oil recovery, but they are interested in energy storage. So we look at CCS, which we call carbon capture and storage. So in this technology, nanomaterials has very many applications, as we are going to see in one of the presentations that the professor is going to make tomorrow from UK. So our interest is to see how we can use the nanomaterials for improving CCS. And all these technologies, I have been partly on them, and I have some batch results. So I'm confident if we keep on pushing with these, we have a better future to have these materials commercialized. So what we look at the end, the HEPSA, the Royal Academy, what is their major aim in this? If we can have students, they can have these tangible skills, at least translated to you can translate them and apply them in the industry. That's why you bring the Petroleum Authority now. And they gave us the oil samples for our fields here in Uganda. We are using the real oil samples. We had the chance, the undergraduate students I worked with them, I think they are over 18. They all worked on Bio-Silica applications. And some of them, I think, prepared some posters which they can share at the end. Though we didn't use our crude oil, by then we didn't have it, but the master students, they're going to use this real crude oil, and we expect them to make a presentation to the authority to show them what we have. So I have done similar studies using various nanomaterials. So we want to use the same nanomaterials, but using our crude oil in Uganda. And then we can be able to know what we are producing. That is an overview of the project. And I appreciate all of you that have made it to come to Mbarara University. And I will be open to any discussion, and hope you enjoy the rest of the discussions we have in our workshop. Thank you so much.
Thank you so much. Ladies and gentlemen, I'd like to share something, but you may have heard it some time before. Bill Clinton visited Uganda, and when he came here, he happened to meet our president. But while they were having a chat at the balcony, and power went off, and that is so common in Uganda. So Bill Clinton was like, oh, well, it happens, it's Africa. So our president visited the United States, and as they were seated at the gazebo, a certain building went black all of a sudden. And then our president, Yoweri Kaguta Museveni, asked Clinton, there's a building that has gone black there. So he called the butler and asked him, which building has gone black there? And the butler whispered, that is the Ugandan embassy. So our problems always come and go. Why am I saying this? We apologize for any inconveniences. It is Mbarara University, we are far. And if anything goes wrong, please, the man to nail is Sagala, not me, and the US. Online, we do have our people present there, and I request again, Engineer Sagala to come and introduce them. I don't want to go wrong with the names, or basically this one from Nigeria, beg. Come and introduce them. They're online, yes.
So with us, we have the partner from, the first one is Professor Chirabida, who is from Makerere. That one, I think some of us know him. Then the professor from UK, you can see from those branch is Annie Mubridge. She's also a professor in the Department of Earth Science and Engineering at Imperial College. Actually, Royal Academy has their offices at Imperial College. So this is why if you get a partner from Imperial College, you stand high chances. And the guy who is the overall lead or the overseer of the Royal Academy is also from Kenya. Then another partner we have is from Namibia, Professor Sheikh Yusuf Ahmad. He's a professor from the University of Namibia. And then Professor Robinson Ejla, and he's from Abubakar Trafa Bailey University. Those are our partners. And then for industrial partners, we have from Namibia, it's called Avgro. It's a horticulture, a very big company which has offices it has departments in South Africa, Botswana, and Namibia. So I have been able to visit that one in Namibia. It's a desert, but they are doing a lot of farming, especially for olive oil and then horticulture, because their land is so dry that any fertilizer I propose to them, they will just test it before they confirm if it works or not. So that's why the market for fertilizers in Namibia and the neighboring areas, it's very high. Then for the Nigeria partner, Professor Robinson, we are looking at the military because we have the connection with their military. We have to make a presentation and then we show them how we are going to decorate our Bio-Silica with some surface materials that have affinity for toxic gases. This is how we can do the chemistry. We play with the nanomaterials and then we incorporate them in making these face masks. Then for Imperial College, the Professor Anne, for them their interest is in CCS. So I think I can now welcome the Dean to give his remarks. Thank you so much.
Dean, I'll bring you the microphone. You're the Dean. Yes.
I got one. Thank you, Dr. Sagala. Thank you, Angela. I want to once again to welcome our University Secretary to the Faculty of Applied Sciences and Technology. I think I'm going to stand. Of recent, I have developed some back pain, and that doesn't allow me to sit for long, doesn't allow me to stand for long, doesn't allow me to sleep for long, doesn't allow me to do anything for long. I want to welcome everyone to Mbarara University of Science and Technology, specifically the Faculty of Applied Sciences and Technology. I'm called Dr. John Sobungoloch, and unlike Dr. Sagala, my area is into biomedical engineering, not petroleum engineering. I had a small interaction with nanotechnology when I was doing my master's degree, and that was into drug delivery, and I stopped there. When the grant ran out, I also stopped. So I hope that Sagala is going to continue with this nanotechnology for several years to come. At Mbarara University of Science and Technology, Faculty of Applied Sciences and Technology, we have several programs that we run at this faculty, and one of them is petroleum engineering that is currently doing this collaboration. I think the head of department, petroleum engineering, is somewhere. Where is Patrick Kabanda? Here. This is the head of department, petroleum engineering. And I want to thank the department so much, because at some time we had started talks about phasing out petroleum engineering from the faculty. The department by then had engineer, who was your the first head of department, Siraji. Siraji did a lot of groundwork and found favor with Makere University, with the Petroleum Authority of Uganda, with several other organizations that are currently trying to do something in oil recovery. And they told him, I think your decision is very premature. The field is just opening up. Why do you want to close now? But we had decided that we closed down petroleum engineering way back in 2021. But as we talk now, if you take stock of our graduates who are outside there, the graduates from petroleum engineering are the ones that are highly placed outside there. So I want to thank the department for working hard, and specifically also thank Petroleum Authority of Uganda. I don't know if the representatives are already here. Yeah, he's here. Yes, thank you, sir, for nurturing Mbarara University into this new field of petroleum engineering. The collaborations that Dr. Sagala is bringing here are of very great value to us, and we want to keep them dear to our hearts, because they bring growth to the faculty, they bring growth to our university as well. So I want to encourage the rest of us as well. Dr. Sagala has already mentioned that there are several schemes within the Royal Academy of Engineering that you can start collaborations and do something similar to what Dr. Sagala and colleagues are currently doing. Our colleagues and partners who are online, we welcome you as you travel tomorrow. We wish you a safe journey as you travel to Mbarara. But we are grateful and happy that you can collaborate with us. We have previously had Engineer Chirabira here, and I think he's nurturing not only Dr. Sagala, but also a number of other staff within the faculty here are being nurtured by Professor Chirabira. So I hear names of several other professors who are online. I want to urge our staff here that hook on to one of them and let's get nurtured. Our faculty has very young staff who still need nurturing and need development. One time when I was attending a conference in Canada, I am a group of the International Society of Magnetic Resonance in Medicine, and we formed a group of senior people to nurture the young ones. And then we said, how do you define the young ones? Okay, because I could be 50, but I still need nurturing. Then they said, okay, the young ones, we are going to define them in terms of research. If you have done research for 5 years or less, then you are a junior person. So it doesn't matter whether you have gray hair like me. If you need nurturing, somebody can nurture you. So I will encourage you to hook on to one of the professors to nurture us up and bring us up as a formidable faculty in terms of research and education. I like the theme of this conference, which talks about bridging the gap between academia and industry. This is our last semester of an academic year, and many students are now coming to my office and say, I have finished my 4th year. Now
will be to characterize Bio-Silica nanoparticles for their physical-chemical properties. My third objective will be to functionalize Bio-Silica nanoparticles with the hydroxyl, amino, and carboxylic functional groups. My fourth objective will be to assess the efficiency of the functionalized Bio-Silica nanoparticles in the removal of pharmaceutical residues from wastewater. My methods, first there will be pre-treatment, which is basically cleaning, drying, name it, and then the rice husks will be acid leached to remove the inorganic pollutants. Then my synthesis will involve burning the rice husks at 600 degrees Celsius in an electric furnace for 6 hours to form ash. This ash will be treated with sodium hydroxide with magnetic stirring for 1 hour, and then the residue will be reacted with sulfuric acid to form the Bio-Silica nanoparticles. My method for the specific objective number 2, which is characterization of the Bio-Silica nanoparticles, will basically, I'll use the Fourier transform infrared, commonly known as the FTIR, for the functional groups, the TEM for the size, the SEM, which is the scanning electron microscope for the morphology, and the X-ray diffractometer for the crystallography of the Bio-Silica nanoparticles. My method for the specific objective number 3, which is functionalization of the Bio-Silica nanoparticles, will include addition of ethanol to the synthesized nanoparticles, followed by aminopropyl triethoxysilane, then followed by the addition of citric acid. My method for the specific objective number 4 will be I'll vary adsorption parameters of adsorption temperature, the pH, the dosage of the adsorbent, and the contact time of the Bio-Silica nanoparticles with the pharmaceutical residues. My work plan is scheduled to run from June to March of 2025. My budget 33 million Uganda shillings. Thank you.
Thank you so much. Next is Mr. Sema Steven.
Yes, protocol observed. Good afternoon, everyone. My name is Semambo Steven, and I'm going to present my topic, which is the determination of the drug loading capacity and release kinetics of doxorubicin using Bio-Silica nanoparticles from rice husks. My supervisors, Dr. Nantaba Florence and Dr. Kenneth Sekatawa. Yes, basically, doxorubicin is an anti-cancer drug. Basically, cancer is one of the biggest problems we have right nowadays in the medical field, and it results into the multiplication, rapid multiplication of what? Of cells due to mutations. So, and they have come up various methods to combat this through chemotherapy, radiotherapy, and by using doxorubicin is used in chemotherapy, which is an anti-cancer drug. Yes, but its use is combated by various problems. Yes, for example, the non-specificity, because remember, with cancer we are multiplying the normal cells. In other words, most of the properties are the same. So the properties and the way this doxorubicin works, it will also affect the what? The normal cells. So this will lead to adverse effects on healthy tissues and subtherapeutic drug concentrations. By subtherapeutic, I mean having a low concentration of the drug at a given site, for example, our tumor, which cannot effect a response. So that insinuates that we shall have to use more of this drug than what? Anticipated. So in my problem statement, the major issue I'm looking towards is to synthesize these Bio-Silica nanoparticles and use them as a drug delivery system for this doxorubicin. Yeah, and I'm using the rice husks as my mode for synthesis because rice husks contains about 70% of the silica content compared to other feedstocks, for example, sugarcane, and it's also cheap and abundant. Yes, so these Bio-Silica nanoparticles, within the field of medicine, they have tried to use synthetic nanoparticles, but this bring about an environmental hazard because they are not biodegradable in the environment. So by use of these bio nanoparticles, it will help us to have an environmentally sustainable method. So for my objectives, my main objective is to determine the drug loading capacity and release kinetics of doxorubicin by synthesizing, characterizing, and functionalizing Bio-Silica nanoparticles from rice husks. Under my specific objectives, my first objective is to synthesize mesoporous Bio-Silica nanoparticles from rice husks. For this project, I'm going to use the mesoporous because of its effective loading and the good pore structure for the maximum loading of this drug. For my second objective, I'm going to characterize the synthesized Bio-Silica nanoparticles for their physiochemical properties in order to enhance the adsorption properties. Then my third, to functionize the Bio-Silica nanoparticles for improved adsorption characteristics, I'll add a functionalizing agent. Then my fourth, to evaluate the drug loading capacity and release kinetics of doxorubicin Bio-Silica nanoparticles in vitro. So under my methods, for my specific objective one, the synthesizing, I'll have the rice husk collection. This will be cleaned and dried. Then I'll do the acid leaching to remove the minerals, to remove the metals from these rice husks. I'll wash with the distilled water and dry them. Then I'll extract silica by calcination at about 700 degrees Celsius. Then I'll dissolve this in sodium hydroxide from sodium silicate. For this sodium silicate, then I'll add my CTAB, which is the cetyl trimethyl ammonium bromide. This will bring about the mesoporous structure, which I want to use for that maximum drug loading. Then after that, I'll add sulfuric acid for my gel. I'll age and dry it. Then I'll calcinate to obtain the mesoporous Bio-Silica nanoparticle. For my specific objective 2, which is the characterization, I'll use the XRD to determine the crystal structure. I'll use the TEM to determine the sizes of these nanoparticles. I'll use the same to get the surface morphology of this. Then I'll use the FTIR to get the functional groups of my Bio-Silica nanoparticles, which have been functionalized. My specific objective 3, the functionalizing. I'm going to use 3-aminopropyl triethoxysilane. Okay, thank you very much.
Good afternoon. As earlier mentioned, my name is Sebulime Stephen, and I'm going to present. My topic is evaluating the impact of amorphous Bio-Silica nanoparticles on nutrient availability in the soil and the growth patterns of Physiolus vulgaris. As you heard in my title, I'm going to use amorphous Bio-Silica. Most of the rice husks have been found to have the highest percentages amorphous silica. And this amorphous silica has been used elsewhere in other countries as a fertilizer from the husks. So I'm going to look at how this Bio-Silica avails nutrients to the soil, which in turn also help in the growth patterns of Physiolus vulgaris. Now, Physiolus vulgaris is just the common beans that we eat every day. And I'm specifically looking at Physiolus vulgaris because it is one of the common plants that people use as food, as a source of protein. So my supervisors are going to be Dr. Nantaba Florence and Professor Antali Mohammed. We all know that rice husks are waste. After removing the rice, most of the time the rice husks are thrown away as waste. So from the Sustainable Development Goals and so many other UN related, we are not supposed, we need to minimize waste. So we can use the husks as an alternative for fertilizers. We also know that the synthetic fertilizers that we normally use have environmental impacts. So here we have the rice husks that are not environmentally degrading. So why can't we use them as alternatives for the synthetic fertilizers that we normally use? So this brings me to my problem statement that states that despite the potential benefits of amorphous Bio-Silica nanoparticles produced from rice husk wastes in improving soil properties and plant health demonstrated when used as natural fertilizers, its application and effectiveness in agriculture remained underexplored. Therefore, chemical fertilizers that we normally use, I'm talking about the synthetic ones, can cause long-term environmental deterioration and are frequently expensive to buy. Those of you who have used fertilizers, we know that. Therefore, I intend to use the rice husks to obtain the amorphous Bio-Silica that can be used as an alternative to the synthetic fertilizers. My main objective will be to synthesize, characterize, and evaluate the impact of amorphous Bio-Silica nanoparticles on soil nutrient availability and the growth patterns of Physiolas vulgaris. The specific objectives, I have 4 specific objectives. Number 1 is to synthesize amorphous Bio-Silica nanoparticles from the rice husks. Number 2 is to characterize the synthesized amorphous nanosilica to characterize the synthesized amorphous Bio-Silica nanoparticles. Number 3 is to analyze the nutrient composition. By nutrient composition, I mean the Bio-Silica extracted from the rice husks will avail nutrients to the soil, which soil will support the plant growth of Physiolas vulgaris. My last objective will be to apply the amorphous Bio-Silica extracted from the rice husks, but also look at the yield parameters of the Physiolas vulgaris after application of that Bio-Silica. The method and materials, specific objective 1, I'll do pre-treatment of the Bio-Silica extracted. That involves cleaning to remove dirt and other impurities, calcination, and calcination involves heating the rice husks at temperatures of around 600 degrees Celsius, and then you mash to increase the surface area of the Bio-Silica obtained from the rice husks. Then you use that Bio-Silica, you apply it in the soil. The specific objective number 2, that was to characterize the Bio-Silica. I'll use the methods I already mentioned, X-ray diffraction to determine the crystal structure, the FTIR for determining functional groups in the Bio-Silica, the SEM, which is the scanning electron microscope for surface morphology, but also the transmission electroscope.
Thank you so much, Stephen and Solomon, yes. So this was the S team. Can I have one of my ushers move the microphone around? You can stay seated. The other time it was the microphone issue. The questions are going to be to you. Question 1, please, ladies and gentlemen. Yes. Lillian, the microphone, please. The Dean has raised his hand.
Thank you. I think my question goes to Salome, but I will also touch on the other previous presenters. And this question is mostly guided by my ignorance of the whole process. You are removing pharmaceutical residues. Another person was removing bacteria. Another person was removing persistent pollutants. Another one is removing something. And my water might have bacteria, it might have pharmaceutical waste, might have persistent pollutants. Do I need these three different things to purify that water? And when I look at the process that the system is going through, everybody is burning rice, husks everywhere, and everyone is leaching them, increasing surface area. Can't one person burn rice and give the rest the ash? Since it is collaborative research. And also when you go into adding other additives, ethanol, citric acid, and something like that. So when you talk of ethanol, everybody knows the price of Johnny Walker. I can start imagining the cost of this thing after it has gone through that process. Will it be affordable for the people to use it actually? So that is my question. Thank you.
Next question, please. I'll take this.
Thank you very much. From the previous presenters to the current presenters, as the Dean has said, when you see the first and the second objectives are more like the same, and from the overview that Dr. Farad gave, it's as if the Bio-Silica has already been characterized, and what remains is mainly the application, the functionalization. So I really don't know if there is a way that the first two objectives can be modified to be unique as far as your own research is concerned. Because if the findings are presented to an audience that may be not knowing what is taking place, it is more or less of duplication for objective 1 and 2. So I would wish to propose that there should be some originality in the first and the second objective. Thank you.
Thank you, Dr. Huntington. Mine will just be a continuation from what Dr. Huntington has raised. I'll just ask the last presenter about this form of the silica, the Bio-Silica that they will use. The first two objectives in every presentation were looking similar, but I want to assume that each of you may need a different form of Bio-Silica. So if that is right, then in your presentation, be very specific on the form of Bio-Silica that you're going to use for that particular function. That takes me to the last presenter. The form of Bio-Silica you will use, if I'm not wrong, is amorphous, right? But the proportion of amorphous Bio-Silica is only like 1% to 2% if you use, that is weight by weight. If you're to use an extraction of, let's say, 30 to 100%. So do you think that that 1% will give us enough nutrients for that fertilizer, or there is some other thesis that you will do to fit your functionality? Thank you.
You take one. Are we done? Okay, we'll start the way we started presenting.
To answer the Dean's question of do you need 3 different forms of biosilica? Yes, we need different forms of biosilica to remove these different pollutants from water. Like the previous person had said, you can have amorphous and the mesoporous. When you go into the methods in details, you realize they differ. So I am dealing with amorphous biosilica nanoparticles to remove the pharmaceutical residues from the wastewater. The second question was, will I be able to afford the ethanol? Yes, ethanol is very affordable. I think that's it.
Okay, thank you very much. From most of the questions I've realized the problem you were saying that most of our first and second objectives are the same. Well, they look the same on paper, but they're not the same because we are dealing with different forms. As you can see, he's dealing with amorphous, I'm dealing with mesoporous. We try for the application, when you look at, for example, he's dealing in agriculture, he will need to use the amorphous because it has those characteristics that we need. I'm dealing in what? Drug delivery. So I'll use mesoporous because I want to increase the surface area, yes, and the loading ratio of the drug. So most of them, they are not the same, and we are using our methods are almost similar, but we're using different reagents and different conditions to come up with these nanoparticles. Yes. Then for the chemicals, the price of the chemicals, most of these chemicals, we buy them in when they're highly concentrated, and we dilute them for use at this scale because the project may take about maybe 6 months. So most of them may be a bit expensive, but we try to dilute to get the proportions that we want. Thank you very much.
Thank you. I would like to respond to the Dean. In fact, I want to add my voice to what she said, that you will definitely need different forms of biosilica for the different applications that you have. The reason why she used amorphous, like you said, or mesoporous is because mesoporous has different properties for that particular application. So you can't use amorphous to do drug delivery because the properties of amorphous do not help you in drug delivery. Concerning the price of chemicals, most of the time methods are optimized for purposes of affordability. You talked of John Walker, is that what you talked? Okay, ethanol. Ethanol is not John Walker. The proportion of ethanol in John Walker might be very low.
Very small.
But ethanol can be manufactured even locally here. We used to use ethanol for sanitizers, so it means we can afford ethanol here locally. Therefore, the price will not be high. Concerning the percentage of amorphous papers that I looked at, okay, not few, but from the literature review that I read, most of the rice husks have amorphous biosilica. Therefore, I believe that the percentage of amorphous biosilica is high in there. But I want to say that I'll read further to confirm your statement. Thank you.
Let's give them a round of applause. Thank you so much for presenting. Right now, we're inviting the final lap, and this includes Kugonza Mpoza, Rutaraka Gideon, and Babide Prudence. Okay, that's fine with me as they're coming, yes.
Thank you so much, Coordinator. I want to add my voice, especially to the questions of the Dean, to what the students have responded. First, he asked about how to remove the nanoparticles from the water, or whether these nanoparticles are not going to become other pollutants. Basically, what we are looking at is that we want to develop nanoparticle adsorbents,
we want to assist or to tap into the water treatment process. Because for now, if you look at the conventional water treatment process, most of these pollutants are not catered for. So that's why we want to develop these adsorbents so that they can be used in the water treatment process. For now, we are looking at wastewater. We are not going to get the nanoparticles and put them in, let's say, water bodies. No, we cannot do that because definitely they may cause harm than good. So what we are looking at today is to first treat the wastewater, because it is this wastewater which is the source of these pollutants into our water bodies. So we believe if we treat the wastewater very well, we shall be limiting the pollution in the water bodies. Then another question was about whether we need the different Bio-Silica for the different processes. For example, removal of pharmaceuticals, removal of pathogenic microorganisms, and the rest. The answer is yes, because especially, for example, if I take an example of removal of pharmaceuticals, these compounds are polar in nature. So if you have Bio-Silica, you need to functionalize it with polar groups. For example, the amino groups, carboxylic, OH groups. So if you just use it, it may not help. Yet, if you're using it with the pathogenic, it may help. And again, you have to optimize which conditions are best for removal of these pollutants. You have to first do that research before you apply it. And it needs a specific study to do that. Then also issue about the chemicals. We are the chemists from the Department of Chemistry. So literally, we have know about these chemicals. They are stocked in our labs. And we are not worried about the costs because this is what we do every day. So we procure them. We are used to that. So that's not...
The issue of cost was for the final user. Finally, when you have made it for the industry.
For the final user, for the industry. Actually, if you talk about ethanol, it is one of the cheapest chemicals, I would say, that we use because it is easy to generate, to manufacture. We can even manufacture it ourselves in the lab. Yes. But again, after all these studies, we want to do the evaluation of the cost, because we want to look at something which is easy, which is affordable, which is environmentally friendly. So we are looking at all those conditions. We are putting all of them into consideration at the end of the project or the study. Thank you so much.
Yes. If the presentation, this is my idea.
Yes.
If the presentations are also all about Bio-Silica, we are finding out that we are losing the most important parts because of that. Yes. That's why we are asking several questions, and the optimization part is not very important. So the part of sample collection and sample preparation is nearly the same. So they just simply need to rush about that and specialize on the form of silica you're going to use, and then concentrate on the other last parts, so that we can get the clear picture.
Okay, right. So in 5 minutes, you cannot say much. Okay. Gonza?
Good evening, everyone. Sorry for that. Good afternoon, everyone. Yeah, I think timekeeper, maybe a little bit, because I wanted to comment about what they are talking about, because they are looking at the various silica classifications we are going to use. And as to me, since we are here to learn, I feel like, for example, my colleague was trying to extract oil, that's spillage. So another person was trying to look at the pharmaceutical wastes. So as per me, I'm also looking at the industrial wastes, the heavy materials. So I felt like after coming to a conclusion, if he tests his hypothesis and it's right, I test mine, it's right. So I think if we come up with a nano membrane, which maybe it can be a double or triple membrane. For example, for the case of the first phase, we have maybe we are trying to eliminate heavy materials. Then the next phase we try to eliminate oil. The other phase we try to eliminate maybe pharmaceutical waste products. Maybe if we come with a system after all this research, which combines everything, maybe we can come up with a product which can be used by any system or any organization, like maybe National Water, as a way of treating our water. I think it works, right? So actually that was my suggestion. So let me start presenting my own proposal. First of all, I'm Kugonza Mpoza. I'm going to present to you a topic which is optimization of eco-friendly heavy metal extraction from industrial waste products using Bio-Silica, nanoparticles from rice husks. So my problem statement: 1, industrial wastewater contains harmful heavy materials such as lead, cadmium, we have arsenic, we have mercury. So all these heavy metals are non-biodegradable, hence becoming a problem or an issue. So currently we have conventional treatment methods such as chemical precipitation, filtration, we have phytoremediation, bioremediation. That's where we use microorganisms to eliminate these heavy materials. Then phytoremediation, that's where we use now plants. We have some plants like, for example, sunflower. It's used to eliminate heavy materials, heavy metals from soil. So, but these plants, after some time they decay. Still, the heavy material go back to the soil or out to our water bodies. So, we are looking for some cost-effective and eco-friendly method which can eliminate all this. So that's why we come to a conclusion that we need some Bio-Silica from rice husks. Of course, as for today, we have a lot abundant resource in our rice husks, because each and every year in Uganda we produce several hundreds of tons of rice. So which means there's a direct production of our raw material, which is going to be rice husks. So my main objective is to optimize. It's not a new project. People have done it somewhere, because these are projects which have already been done by some people. But we are trying to look for which way can we optimize. How can we optimize our Bio-Silica to extract more of these heavy metals? Because we are looking at the standards of World Health Organization, which kind of allowable heavy metal measurements are allowed to be within our consumable water. So another thing is my specific objectives here. I'm going to determine also the physical chemical properties of the rice husks I'm going to be using. Then I'll mainly look at maybe roofing. Also, I'll use also the XRD same term for various surface analysis, porous. So I think just because of time, I have an activity plan which is going to run for around 6 months approximately. Then also I have a budget which runs up to around 34 million. So thank you so much.
Yes, good afternoon. My name is Gideon Rutaraka, and I'm trying to develop a bio-based flame retardant from rice husks Bio-Silica for application in polyurethane foams. Now, these polyurethane foams are used in many applications, We use them in furniture as cushions. We use them for mattresses. And we also use them for thermal insulation. Now, these polyurethane foams are highly flammable. And when fire breaks out, what we have is loss of property. That is one. We are going to have loss of property. Let me stand aside. We're going to have loss of property. And then also because of the smoke, as people inhale the smoke, we have loss of lives. So my problem statement looks at the flame retardants that are currently on market. What we have on market are halogenated flame retardants, those that have been manufactured from halogenated compounds, for example, like chlorine and bromine. Now, these ones pose a significant environmental and health risk. And as the fire propagates, or as the flame propagates, we are going to have a lot of smoke that can be inhaled and lead to loss of life. So the flame retardant that I'm trying to come up with, which is bio-based, we are going to use a biomaterial. And this biomaterial will be more environmentally friendly and reduce on the health risks that are posed by these traditional flame retardants. Now, there is need to develop a bio-based alternative that is both effective and environmentally friendly, and that is what I'm trying to work on. Now, the polyurethane foams I'm talking about is something like that. They are used in our cushions, that is furniture. They are used for mattresses. And they also use it for thermal insulation in buildings. Can be used as building materials. Next. Now, my main objective is to develop a bio-based flame retardant derived from rice husk Bio-Silica for enhancing the flame retardancy of polyurethane foams. Now, my specific objectives, I'll first begin by extracting the Bio-Silica from the rice husks, characterize its properties, that is both the physical and the chemical properties. Then I will develop a bio-based flame retardant using the extracted Bio-Silica, and then evaluate the mechanical properties. After I've incorporated it in the polyurethane foams, I'll be able to evaluate what effect it has on the mechanical properties, thermal properties of the polyurethane foams, and also on the flame retardancy of these treated foams. For the extraction process, the raw material is the rice husks, and these will be secured from a local agricultural source. Then the method I'm going to use for extraction of Bio-Silica is the salt gel method, and these are the steps for the salt gel method. Then when it comes to characterization, I'm going to be looking at both the physical and the chemical properties. And for the physical properties, I'm going to use the scanning electron microscope for the morphology. And then for the chemical properties, I'm going to use the FTIR. That is for the characterization of both the physical and the chemical properties of the extracted Bio-Silica. Then next, when it goes to the integration of this Bio-Silica into the polyurethane foams, after I've incorporated the Bio-Silica into the matrix of the polyurethane foams, I will do some performance tests or performance evaluation tests on these treated polyurethane foams. And one of them is the cone calorimetry, which will evaluate the flame retardancy. Like I said, I'll be looking at both the thermal properties of the treated polyurethane foams. I'll be looking at the mechanical properties, because most studies show that when you incorporate this Bio-Silica, other studies have been using this conventional silica, it actually has an effect on the mechanical properties. So I will look at all that, and that's why I have tensile testing that will help work on the mechanical properties. Then I have the limiting oxygen index. This one will give me a view on the amount of oxygen needed to sustain the flame. Then I think we can go to the next. Next, please. those are the tests. Then I'm hoping to run this project for a period of 10 months. So it will go up to June next year, 2025. So that is my budget. Next, please. Yeah, that is my budget, and it sums up to around 10.8 million. Thank you.
All protocol observed. A good afternoon to you all. I'm Babide Prudence Mary, and I'm going to give my presentation about synthesis and evaluation of the effectiveness of Bio-Silica nanoparticles obtained from rice husks in aphid pest control. Okay. The main reason as to why I'm carrying out this research is because generally there is a great use of synthetic pesticides, which synthetic pesticides are basically chemicals. So literature says Bio-Silica has pesticidal properties. So I'm going to incorporate Bio-Silica as a pesticide in order to control aphid pests. So by doing that, I'll be able to improve food security, and also as the SDGs says of responsible consumption and production, that's SDG 12, I'll be able to improve the yield of the crops with less use of harmful pesticides. Okay, next slide. So the first objective is to synthesize and evaluate the effectiveness of Bio-Silica nanoparticles in aphid pest control. And the specific objectives, one is to synthesize both mesoporous and amorphous Bio-Silica nanoparticles from rice husks, then to characterize the mesoporous and amorphous Bio-Silica, and to assess the effectiveness of those two, amorphous and mesoporous Bio-Silica, on pest control. Okay, for the specific objective one, which is synthesizing the Bio-Silica, I'll have, this is the flow diagram of how it will be carried out. There will be acid pretreatment, rice husk pretreatment. I want the rice husks to become the Bio-Silica nanoparticles. So they will go through those processes, and I will be able to form both mesoporous Bio-Silica and amorphous Bio-Silica. Then for the second specific objective, there will be characterization of the mesoporous and amorphous Bio-Silica using the scanning electron microscope, the transmission electron microscope, and the XRD. The scanning is basically for the surface morphology. Then the transition electron microscope, it's for the particle size, and the X-ray diffraction is for the crystalline structure. So these two, can I go back to the previous slide, please? These two can be distinguished in their structure. They are because mesoporous Bio-Silica is crystalline and amorphous is non-crystalline. So at this point, I'll be able to identify. I'm using both because I want to know which is best for agricultural purposes. Next slide. Then the third objective is to assess the effectiveness of this Bio-Silica nanoparticles on pest control in aphids. So I'm choosing aphids because they affect the plants. Aphids are pests. So when those pests go onto the plants, they will cause them to become yellow. They will bring black spots and affect the productivity or the yield of that plant. So I'm using aphid as a control, and in the method that I'm going to use for aphids, I'll just culture the aphids. Then after culturing the aphids and they grow, I'll get different Bio-Silica and a standard of a synthetic pesticide, which I know has to have an effect on the pest. So I'll use the two different Bio-Silica and the standard, and the control, which will be the synthetic Bio-Silica, and I see how effective that Bio-Silica is as a pesticide. Next slide. So that is my work plan, and it will run up to January 2025 if all goes well. Then the budget, that is the budget for the project. Thank you.
Questions are welcome. Remember, you're standing between us and lunch as you're asking the questions. Did I scare you? Did they present well? Yes, Dean. Yes, there's another hand there.
The gentleman in the middle, I think I was a little bit not attentive. I didn't get your presentation very well. Could you just summarize it for me in a minute or so, what your research is about? And then Gideon, is that Gideon? Maybe somebody talked about the quantities here. Maybe you can elaborate a little bit for me. How much rice husks do you need to get what quantity of Bio-Silica?
Another question, please. There's a hand there and there.
Thank you. Maybe as they're answering the Dean's question, I would like to ask if they're developing their own methods or they're using already existing methods. And my next question would be based on the answer I get. So I think I will come later when that is answered.
Okay, let's have that question there. I request Lillian is helped so that she gets ready for the next presentation.
Yes, I'm just emphasizing on the point Dr. Harrington raised about the specific objectives, the first one and second one. No one paid attention to it. It was like, could there be another way you can modify your specific objective so that they can look unique, not having from first presenter to the last presenter having the same objectives 1 and 2. Thank you.
Yes, moderator, okay.
I just wanted to make a comment on that. Actually, I forgot. I can be corrected if I'm wrong. Just take an example of Irish potatoes. We're all synthesizing Bio-Silica, right? But when you look at Irish potatoes in, let's say, Kabal, and Irish potatoes in, let's say, Masaka, are they the same? They're all Irish potatoes anyway. They're different species, not so. Therefore, the reason why we all characterize this Bio-Silica and do all those other, the first two objectives, is because they are different. The rice husks I'm going to use may not necessarily be the rice husks she's going to use. Therefore, I can't stand here and say they'll give me the same properties or they give me the same quality of Bio-Silica. That's why we have to characterize them and know what kind of Bio-Silica do they have. Is it the one that can do the pesticidal properties that she wants? Are they the ones that can do the fertilizer bit that I'm doing? So it is important that each of us characterizes the Bio-Silica that they have. Thank you.
I think you didn't quote me right. I didn't say you should not characterize. No. where like the way you wrote, all of you have the same statements, 1 and 2, almost for all of you. Where like, is there another way? You can just reframe your objective. Just reframing in line with what you are doing so that you can be direct, more direct actually. Thank you.
Yes, thank you. Thank you for the questions. On the issue of the objectives, I think those can be modified with time as we work with our supervisors. This is not the final work. We shall take that into consideration when we come up with when you are coming up with the final proposals. Now on the issue of, I asked how much can we extract, how much do we need? From around 500 kilograms, from around 200, we can get 50 kilograms of Bio-Silica. And for my case, I chose this sol gel method because I'm trying to look at something that is environmentally friendly. Yeah, because that is my main goal in my study, to do everything environmentally friendly so that I can conserve the environment as I do this study. Thank you.
Okay, thank you, Doctor. We talked about my topic. Actually, my topic, I'm trying to extract or remove heavy metals from industrial wastes. So in this, I'm going to optimize the Bio-Silica from rice husks so that I can remove most of the heavy metals from the industrial wastewater. Yes. Thank you. Okay. I think she doesn't have. Okay, let me say something. There's something actually, you know, as I was seated here, I thought of something that would help us maybe in future. Because I looked at, everyone is like, you are producing Bio-Silica, but you know, okay, yeah, we're doing different, we are doing various things, like we're applying this silica in various stuff, either maybe to extract this and this, but I thought of, if this comes to the end and we are successful, I felt like maybe we can initiate a project whereby we integrate this kind of Bio-Silica from various projects. We integrate it into one so that we can use it for a single use, maybe for on an industrial scale. Perhaps not using the nanotube, the nano particle membranes. Then we can try to integrate all these Bio-Silica nanoparticles. We integrate them into one so that we can use it to achieve a better thing. Thank you so much.
A round of applause for this. Oh, sorry, no. Okay.
My question was not answered.
Yeah, Doctor had a question first. Your topic then is going to ask you the questions. Then about the percentage, then he has a question after how much you're going to get. Then maybe I'll come in later.
Okay, I think his question was, were these methods developed by us? They were not developed by us. I think that's a correction we shall have to make. I think he wants us to cite on the slides. We shall have to correct that. Thank you.
Okay, that wasn't my concern, but I just wanted to know if the validations were done, if it was, if the analytical method development procedures were right, and so on and so forth. But it's okay. If this is a standard method and procedure that you're following, it's okay. And then we have several pesticides on the market. How different is yours? Yes, we are looking at waste minimization, but are we looking at the ecosystem, eco-balance, and biodiversity? We are killing these pests, but do we need them in the environment? How do we like repellents and they still live? We need them. So how different is your pest from others?
Yes, thank you for that question. My name is Ronald Kaiwa. Basically, in the field of nanotechnology, we've had cases where we we are creating a solution and then causing more issues. And that has always manifested in most of our work. And thanks for that issue of biodiversity. We're trying to eliminate the pests, but at what levels? I mean, at what rates? Are we engaging in maybe someone to do with the study of insects? Are we trying to look at the environmentalists? What are they talking about this? So at this level, when we are crafting our proposals, these are very good ideas for us really to think about. Like, you really chew on something, they're like, what am I doing? I'm creating a pesticide. If I characterize this and get the chemical properties, are they only targeting that particular pesticide, or they're actually going out there in form of fumes and doing more harm than good? So these are issues, I think, as students, that we should stomach, go and ponder on, and make sure that when we are crafting these proposals to get to the international level, because these studies are going to really give us good publications. And so these are the concerns that always come, even for some of us that keep submitting papers to those international journals, okay? So as students, let's take these with actually good heart and think about them, okay? So that then we are clear on what we are doing. I've seen this happening many times. When I was doing my activated carbon, the one with the highest ever reported surface area in the world from cassava peels. And someone said, you're treating this wastewater, but then what happens? It was a very simple question. What happens after you've removed these pharmaceuticals? How then do we do the reverse of adsorption to make sure that now these absorbed pharmaceuticals can be disposed of somewhere? Because you're not going to dispose of this activated carbon with, again, the what? The adsorbates. So these are the things we keep chewing on, and they keep generating new research questions for us. And as we are heading into this other presentation, these are things we need to really highlight when you are, because nanotechnology is that catchy, and we think everything nano is really doing us good. But some of these solutions keep generating more problems to us, okay? And so we, as scientists, we keep our minds open. Thank you.
Okay, like I had said, I'm going to work, I didn't talk about it because of time, but I'm going to be working with an entomologist, and I'll have to get permission from the National Council of from the Uganda National Council of Science and Technology to be able to use the aphids, and I'm going to be culturing them in the lab so that I exactly target the aphids and I do not affect the other pests. So if the Bio-Silica works out as a pesticide, then future research would be recommended to use it on other pesticides, on other pests. Thank you.
Maybe just for clarity, this is experimental and lab work. Okay.
Maybe to add on that, whether Bio-Silica, if it succeeds as an option for a pesticide, actually this will be a green option, because if you look at the synthetic pesticides, most of them are the sources of the persistent organic pollutants. These compounds, when they get into the environment, they will live for decades and decades. And they'll even be modified into other more dangerous forms. So those are the synthetic pesticides. So if Bio-Silica succeeds, actually it will be a greener alternative, because it comes from natural sources. And also those synthetic pesticides, the process of synthesizing them, a lot of chemicals are released into the environment, yet themselves as the pesticides, they are a very, very big problem in the environment. Some of the pesticides have been burnt, like, let's say, 20 years ago, but they are still in the environment because they are very, very persistent. So for sure, if Bio-Silica succeeds, it will be a better option than the synthetic pesticides.
Thank you. I'm Chigos Moses. I would say one of the experts in this biomass. I've done biomass quite for some good time. The questions you're asking these students, I think they got the notification, I think, like a month back or less. They are trying to read, okay? And in their reading, they're still reading, they're just trying to explore. Like the issue of characterization. They're picking from the literature and putting it there because they need keep pushing, okay? But for uniformity, because they said they are all uniform. Since you're doing different applications, just look at that property you want to look on, like heavy metals. What makes silica to attract heavy metals? I think put that one into your objective, that I want to characterize this property for this, okay? Not general characterization. Maybe we may get more in my talk tomorrow about characterization of these bio materials from biomass, okay? Because most of the machines you're even mentioning, they're not even in East Africa. That's the challenge I found when I was starting my PhD. We had no XRD, no SAM, no what. And the farthest, the nearest was South Africa and West Africa. So, but lucky enough, they are there. So just focus on your final application. Pick the property you want to use, okay? Because if it is water purification, you know what you're interested in, which is different from heavy metal. Doctor asked about the particle size. These people, they cannot even define the definition of nanotechnology for now, because it just landed on them and they are still trying to figure it out. So they cannot know which particle size do I need for water purification, okay? So kindly just forgive them, just know that they landed on this opportunity within a month and they are trying to do their best. Because I've been with them and they were asking, I said, oh, it can work. Yours, I think you may hit a dead end. So give them time, just give them hope, because they're just starting the journey. You know, when you're starting the masters, you're starting the journey because it is more of self-supervision. Thank you very much.
Thank you for the encouragement. Ladies and gentlemen, we're in Mbarara University of Science and Technology, and we have a faculty of medicine, and they say when you sit for long, it's not healthy. I'm just requesting you to stand up, just stand up, please. We'll stretch a little bit. Yeah, do you have a paper? You have a paper? Yes, people are already stretching out. Okay, the main word here is, I think let's take Bio-Silica. We're writing this with our bodies and writing only capital letters. Start with B, go down, down. Yeah. What are you writing? Up. Give me this. Give me the big stomach. Yes. Hey, you people are lazy. I. Down, 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 up. Okay. Then we take O. That is Z. That is Z. Fortunate. Okay, let's go. O. That way, that way, that way, that way. Yes. You got it? Lydian, you're getting here. Next letter is S. Give me the S. Give me the S, give me the... What's wrong with that team there? Huh? What is that you're writing? You ladies, okay? Let's go I again. Down, up, tip. Okay, L. Down, then move. Make the L. Move. Okay, I. Down, then dot. Give me the C. Give me the C. Joseph, what are you writing? He's writing Q. Give me A. Down, down. Man, I look at the deal. Look at the petroleum guy. And that is hard. Okay, do you have a paper, please? Do you have a paper? You have a pen? Okay, just raise it like this. Okay, put it at the back of your neck. Okay, face someone. Face someone? Okay, draw their face. Start with a circle. What are you doing? Put the circle. Me, I teach Sunday school. Draw the circle. Put the eyes. Put. Sagala, what are you doing? Okay. Put the eyes. Yes, thank you. Put the ears. Put the hair if they have hair. Aish. Put the glasses if they have them. Show them the picture. Is that how they look? Is that how they look? Ladies and gentlemen, in just 10 minutes we are having Lillian, and then we shall have a presentation of, let's take our seats. We are going to have Professor Kirabirai's presentation given to us by the person he has delegated. Lillian, can you do this in just 8-10 minutes? Lunch. Okay.
Good afternoon. Once again, I'm Lillian Akampa, Research Secretary for this project, and I'm just going to give a basic highlight on what this project is about. So the theme is harmonizing innovation, collaborative synthesis of biosilica nanoparticles derived from rice husk for various industry applications. So I think the main words are biosilica, nanoparticles, rice husk, and I'm going to just give you a brief review about the next slide. Next. Yeah, so biosilica is just a term used to refer to the silica compound found in biomass ash. And what is biomass? This is matter from recently living organisms. For example, wood, animals that have died. And when they are burnt, the ash that is got from them usually contains silica. So plants from certain families, for example, those listed here, contain high levels of this biosilica in their tissues, and it's usually deposited in the form of hydrated silica. So why silica? It has a versatile commercial value. It can be used as a raw material in very many sectors. For example, ceramics making, in biomedicine, in construction, in drug delivery, so many applications. So the most common sources of silica are usually grasses and sage, and they include rice husks, wheat straw, corn cob, bagasse, and very many others. So our project is basically using rice husk. For any given amount of rice husk you burn, it usually yields around 14 to 20% of ash, and this ash contains about 80 to 95% silica, but it's usually in its crystalline form, but it usually has impurities. What are nanoparticles? These are materials that are very small, and their dimensions are all in the nanoscale, under 100 nanometers. Usually that is the size estimation. And because they are so small, they have a large surface area to volume ratio. They have a high chemical and physical stability, and these properties are desirable for their use, either standalone or in combination with so many molecules for their applications in the different industrial work. Next. So I'm going to take you through the synthesis of biosilica. We've heard about this through all the presentations that have gone around today. And this method is not absolute. It can always be changed according to the type or size of silica nanoparticles you want. So this method is according to Gobani et al. That is a group of people that performed the synthesis of biosilica from agricultural waste using an environmentally friendly technique. So it starts with collection of rice husks. These rice husks are usually dirty. So they are washed with distilled water, which is also called deionized water. That is to remove dirt and impurities. After washing them, they are dried at 90 degrees Celsius for 1 hour. That is to remove the water. That is followed by pre-treatment with an acid. Usually, here we're using HCl. What is the importance of pre-treatment? That is to remove metallic impurities. Usually the rice husk has impurities which cannot be removed by just water. So these ions dissolve in the acid and then they can be retrieved. The other importance of pre-treatment is to remove carbon. Before these people did this experiment, they had faced a challenge of unburnt carbon that remains in the ash. So pre-treatment helps remove that unburnt carbon. And then the rice husks, after treating them with the HCl, you wash them again, and that is to help and remove the metallic impurities that have dissolved in the acid. And then we do calcination. Calcination is basically combustion in controlled environment, usually in presence of a very limited supply of oxygen. And we are doing it at 600 degrees Celsius for 6 hours. And why 600 degrees Celsius? It was proved that this is the best temperature if you're to obtain the desirable size and type of nanoparticles. Okay. So after combustion, we are going to obtain ashes, and these ashes, as we said, they contain impurities. They still have impurities. Yes, and then the ash that we've obtained contains sodium silicate. That is the silica, silicon dioxide. And we treat these ashes with a solution of sodium hydroxide to produce sodium silicate. And then this solution above is filtered, and then the filtrate is titrated with sulfuric acid up to a pH of 8, at which the silica gel precipitates out. So that obtained gel is left to stand for about a day, that is 24 hours, and then we do centrifugation to separate the precipitate, that is the gel, from the sulfate salts, from the sulfuric acid. And then we filter our material, wash it to remove the sulfate ions, and then dehydrate. There are very many ways of dehydrating, for example, freeze drying. And after that, we calcine our material once again, and we shall obtain the silica nanoparticles. Next. So these are some of the methods of characterization. FTRI, that is Fourier transform infrared All right, I'm going to use the abbreviations. So the FTIR, it is a technique used to identify chemical bonds, functional groups that are contained in a material. Then TGA is basically used to find out the composition and the thermal properties of a material. And then XRD is basically used to identify the crystalline structure of a substance. DLS, that is dynamic light scattering, and it is usually used to determine the size distribution of particles in a solution. SEM and TEM are used to analyze a material at its atomic structure, usually at the surface for SEM and in the inner core for the TEM. Thank you for listening.
Yeah, thank you so much, Lillian. That was quick and brief. This moment, ladies and gentlemen, allow me to welcome. He will introduce himself, the person going to give us the presentation by Professor Chirabira. And I'll just say Ronald, not Mayinja, but the engineer. Please, the presentation, and it's all right. You can.
Thank you. Good afternoon, everyone. Yes, my name is Ronald Kaiwa. I'm a lecturer at Mackay University in the Department of Mechanical Engineering. My research interests are in biomass valorization, basically looking at how we can use biomass to curb recalcitrant adsorbates, recalcitrant contaminants like pharmaceuticals, some heavy metals, and we are looking at how best we can do this in a very eco-friendly way. So I'm a lecturer, as I said, but I also do other works with Uganda National Bureau of Standards, and I'm the chairperson for the Technical Committee on Production and Engineering Standards and Uganda National Bureau of Standards. Then my colleagues, and they'll be giving us today Baptist Chirabira, our mentor, and we are going to go through some of the collaborative research opportunities that are available. And part of that presentation really kind of ushers us into what the previous speaker, the immediate previous speaker, was talking about. What do we know about nanotechnology? How does it come out from the science, and then we get the technology and we apply it in the different fields. Then we shall look at the research that is ongoing at the African Center of Excellence in Materials, Product Development, and Nanotechnology. Basically, when we talk about nanotechnology, we are talking about nano. We are talking about 10 to the power -9 of a meter. Okay, and so as some of the questions that were being asked to the students, they may not be knowing at this level what is the level we are working with, maybe for water treatment, maybe for drug delivery, but many times we are looking at 1 to 100 nanometers in that field. And then we have other cases where we are looking at actually to the power 10 to power 4. That means we are reducing it to 10 to power -5, okay? So at that, along that scale, different purposes come in, and we are glad that we've embraced nanotechnology in Africa. So it actually goes way back in around 1975 when we had the first lecture, and which formed the framework for nanotechnology. And then we saw it evolving up to around 1980s, where we had the first scanning transmission microscope, which then further formed these two, the scanning electron microscope and then the transmission electron microscope at that level. But nanotechnology actually spans across a number of disciplines, as we shall see. Let me hope the presentation will come in here, but we are not going to dwell more on the science, because it appears that in this room, at least we have a glimpse, and now that I'm standing between people's lunch and where we are, I think we shall not waste a lot of time here. So what we are talking about now is how do we leverage what we have, the knowledge we have, and how do we make it work for other fields besides what we've heard from the different speakers before. Like Dr. Sagala said, we can apply it maybe in petroleum refining, or we can apply it in form of fertilizers. Like now for my study, we are applying it to remove pharmaceuticals from wastewater. And I was talking to Dr. Natava here, who has done a lot of work around pharmaceuticals. But the issue is, how do we remove that in a cheaper way? Not actually using chemicals, but actually an eco-friendly way, okay? So what we are working on is actually customizing some of these materials for a particular purpose. And that's why many people have been talking about having similar objectives. You know, everyone coming in to present, they have almost the first two objectives reading kind of similar. But then how do we really characterize something for a particular purpose? That's the task we have as nanoscientists, as people working in the nanotechnology field, okay? And my idea here is you need to understand, first of all, the base material that we are working with. If we can, that's why everyone wants to characterize. We want to understand the base material we are working with. If I'm doing rice husks, okay, the genetic properties differ. The rice husk in eastern Uganda differs from the rice husk actually in western Uganda. So we need to understand the base material we are working with and really characterize it to the fullness, but be particular on that purpose. Because if you say characterizing rice husks, for what? You see, I was telling people that even color is a characteristic, okay? Odor is actually a characteristic, but what are we characterizing that for? That's why then the gentleman there asked, why are we doing all this? For what? If you say you characterize this for the removal of heavy metals, someone will be particular and will be willing to know, why is he not characterizing the appearance? Why is he not focusing on the appearance of the material like color? Because the focus is now on the surface area, okay? Because we are trying to see how do we remove these recalcitrant heavy metals from water systems, okay? The other thing we would want to look at is, even if we have nanotechnology as a prevalent and a catchy subject, what is the other negative side of nanotechnology? And many people do not want to talk about their babies, okay? When you go to visit someone in a hospital, you always want to say that, wow, the bouncing baby girl, bouncing baby boy. So if someone comes in and says nanotechnology is that bad, okay? People don't want to talk about such. We always want to run with the positivities. But what we are saying is that we should also look at those other anomalies that come along the process. For example, everyone is burning. How much are we producing? How much are we contributing to the carbon footprint through burning? Everyone is saying we are going to burn rice husks, okay? Is someone interested now in studying the life cycle, okay? Can we do a life cycle impact assessment, okay, on just this process and then document it so that it informs maybe people in policy, other researchers on what should not be done, okay? The beauties we have is that we report good results in publications, okay? We only report good results in publications. But no one says that, for example, when we are doing the high surface area activated carbon, okay? What happened with the burning? What happened when we pre-reached the pills, okay? With hydrochloric acid and sodium hydroxide, okay? What happens if the activated carbon is applied in removing pharmaceuticals? And then we have this bulk of the activated carbon, but then intercalated in there, within the matrix, okay? Within the lattice, we have pharmaceuticals. Where and what is the end point? Where are we disposing of this? Okay? So those are the issues that should actually help us with the research. So without wasting time, I would run through this, and I think, yes, let's get to the first slide. So as I was hinting, we are talking about 10 to power negative 9. Whenever we're talking in nano, we are talking about 10 to power negative 9. Okay? That's a nanotechnology. And if we say we are using a scale of 100 nanometers, that means we are just reducing it to 10 to the power negative 7, okay? That's the level we are talking about. Please move. And so nanotechnology is where now we apply the science of understanding a material at a scale of 10 to power negative 9. Why do we do that? Okay? Because we want to have a material that can be tailored to a particular purpose, and working with an atom at a level of 10 to power negative 9, we can always do a number of adjustments to suit a particular purpose rather than working with a whole, okay? So that's why we are building now smarter, cheaper, cleaner, and more precise products using nanotechnology. So let's move. Okay, so the science there, and so within our normal science, that's why the questions we are being asked mainly from the research we have currently. We are working with 1 to 100 nanometers mainly, okay? And so we are looking at one-dimensional materials, okay? Like the dots, okay, the carbon dots. We are looking at two-dimensional materials, like where you would have graphene, and then you build on the two-dimensional material to come up with graphite, okay, which is three-dimensional. And so those nanomaterials are the ones that actually have constituents at nanoscale, and then we go ahead and apply them in a nanotechnology process. Okay, let's move. So this is the history I was giving, and I think we don't have to go through that. Let's move faster. Okay, the revolution of how it has actually been coming through up to this level, where we have a valuation of about $79.14 billion as of 2023 that is around this nanotechnology. Okay, so it's a catchy area, it's a profitable area, and many people are looking at investing in this field, okay, in the different fields. As you can see, the distribution around this, where we have chemical manufacturing, pharmaceuticals, electronics, aerospace engineering, and materials for other purposes, even in the construction industry. Let's move. So when we're talking nanoscale, as I was hinting, different materials, different purposes, okay, we can look at that scale ranging from that, as you can see, up to the level of coming up with a tennis ball. But at the level where we have water, a water molecule, analyzing a water molecule, or at the level where we are doing nanoscale biomolecules, like the presentations that my colleague Dr. Sekata will be giving, on how we can handle that at that level, depends. So when someone is told to do activated carbon, and they ask, why did you have to produce activated carbon at the level of 10 to power -1? Was that necessary? Wouldn't we produce activated carbon at a level of 10 to power 4 and then it would still work? Those are the key questions that come up in research. And so, like, you have some other nanostructures like the dendrimers that come up like with the tree branches, and then you have other polymers coming through, as we shall see. Like my colleague Dr. Iga will be talking about some of the membranes. Then at that scale, you can choose what you want to do. Take the example of a pencil tip at the scale of 10 to power 6. So that means we are reducing that to 0.003 of a what? Of a nanometer. So at that level, we focus on different ideas, and trust me, depending on the equipment we have, depending on the structures we have, their levels we may not attain. Okay, but I'm just saying that don't throw away such work. It informs a lot, because one time we tried to actually get nanoparticles at 10 to power 1. We failed, but we published a paper around that and why we failed. Okay, so I always tell my students, learn to publish why you did what, why you failed. Okay, let's move. So let's compare this. Maybe a sheet of paper is about 100,000 nanometer thick. A sheet of paper, okay, as thin as it is, just 100,000 nanometer thick. But then you take the example of 1 nanometer, where we're talking about 10 to power -9 at that level, where you can adjust the material to whatever you want, introduce new functional groups, and manipulate it in different shapes. You can even do different building blocks in a form of like down, up, and up, down. You can actually do abrasion and get thinner particles, or you can build from particles and get a block, okay? Then it can be in the bulk or on the surface. That's why someone was asking, can't we have something that can actually remove these without introducing the particles themselves, but just having a surface membrane? Okay? I think they didn't ask what happens now to the nanoparticles if you're using them to treat what? To treat water, because some of these nanoparticles will have like silver content in there. Okay? And silver is one of the heavy metals that is actually disturbing us in water systems. Okay? So those are the cases we look at. So let's move faster. Okay, this is still about the schematic idea of the nanoscale and what really happens. So look at the full stop here. It is like a 1 millimeter. Okay, but then the red blood cell is around 5 micrometers. Okay, but when you look at the 0.5 nanometer at the level of the benzene ring, at that level, and even the carbon nanotube, these are different applications, and depending on what you want to do with that material, you can target a particular scale for your work. Okay, rather than wasting a lot of money trying to refine something where you maybe you won't actually attain that level, but you can look at this. If I do just a simple thickness of this watermelon, I can get a 10 centimeter slice out. Okay, but then you look at that scale, and that is the schematic idea of a nanoscale. How better do we come up with materials that we can actually twist? I always use that word, twist around, change shape, change functional groups, and actually tailor them to a particular purpose. Okay, let's move. Okay, so at the nanoscale, we have better properties like increase in surface area. Look at this whole tube, 1 centimeter, you can get a total surface area of 6 centimeters squared. But when we break that, maybe in an abrasion process, and we break that, we can get a total surface area of 1 millimeter tubes. But when we break that further into powder form, it goes on increasing, okay, to 60,000 centimeters squared. And so with that increment in surface area, we can actually use that for different purposes, like in electronics, where we are doing microchips, okay, good microchips using graphene, okay, at that level. And I was talking to someone that the latest microchip, the M3, that is used in some of the good laptops we have, okay, is so small that you can't imagine that it's the one supporting all the work on the piece. But that's because of what? Nanotechnology at that level. So why nanoscale? We can actually have increased surface area, and then if you're handling something in bulk, it's not easy. I give examples to students that if you want to give a good counsel to students, you actually have to do what? Have a one-on-one. Because if you're handling a class as a whole, you may not really get to a particular cause or to a particular element that you want to address in a particular individual. So what we were looking at is, if you have it at a nanoscale, you can adjust it easily. Next. Okay, so besides the surface area, you can get better electronic properties. You can increase the optical band gap, like someone who is working on actually using nanotechnology to improve the surface, the absorption of light intensity in solar cells. Okay, such research. Then you can change the thermal and chemical stabilities, and then you can also play around with the phases and also the catalytic activity, like the metal catalysts. Okay, you can actually do it better when it is at a nanoscale, and even the surface energy increases. Okay, so let's move. Okay, so this I've already talked about it, but I just wanted to flash this out. So look at this, the application in solar cells, or you can even increase the antibacterial properties. That's one that Dr. Sekatawa will be, I think, hopefully, because I know he does a lot of work around this. And then increasing the surface area at that level, and even you can do the magnetic separation. I had someone who is doing something around this. So this is really the whole purpose and the effect that nanotechnology brings in. From the bulk of the material and doing nanoparticles, all these are well affected. And so when someone asks why nanotechnology, these are the causes for nanotechnology. Let's move. Okay, so look at this. This is zinc oxide, and it's one chemistry, many shapes for different applications. You can get dendrimers, okay? You can get actually catalysts, okay? You can get membranes from one chemistry. But at nanoscale, you can actually restructure it into, we can get carbon tubes, we can get carbon rings, we have what we call carbon spheres or carbon balls, okay? You can actually adjust the number of these. Okay, when it is at a nanoscale, but the same chemistry of zinc oxide. Okay, so let's move. So these are the ones I was talking about. At nanotechnology, someone was asking me, what do you mean by 0 dimension? does it even exist? Even when we get to the vector science, does one dimension exist? Okay? Does zero dimension exist? In other words, like zero dimension, you don't move in any direction. You don't move along any axis. So at nanotechnology, we have zero dimensional nanomaterials like the colloids, like fluorines, and then those other quantum dots I talked of. Okay? But then at one dimension, you have like the nanowires, nanofibers, then the carbon nanotubes. But always, for most of our work, our interest always comes around here. How do we handle the two-dimensional nanomaterials and then be able to build different layers on top of another, okay, for the different purposes, and then come up with three-dimensional nanomaterials like the dendrimers, okay, like how you can come up with graphite from graphene, which is two-dimensional, okay. So these are the different classifications of nanomaterials based on their dimensions. Let's move, okay. And so we are within the classifications. These are the ones I've talked of, as you can see. This is one dimension, zero dimension, two dimension, three dimension, and then you can see the morphologies that come up. That's why many of the students are interested in understanding, especially the mechanical students, are interested in understanding the morphologies, okay, of these. How are they appearing? What is the surface? Okay, like if I'm going to do a surface membrane and I'm just coating a particular surface with these nanoparticles, okay? So these are the different classifications of nanomaterials based on dimensions and what they bring to the table in form of applications, okay? Let's move, please. Okay. And I think, yeah, we've already looked at this, okay? Some of them can occur naturally. For example, when we are driving our cars, okay, and we have the tail emissions, some of these cars emit diesel nanoparticles unknowingly, and that's kind of man-made. But then there are some that are occurring naturally, and there are others that can be actually engineered. What we are doing is now we are engineering and changing these properties. But for example, the emissions from our tailpipes, okay, you actually have no idea of how this is working out. And then we can engineer something maybe for the catalytic converter, for the mechanical people, okay, and improve that. So, but our focus is now engineered nanomaterials. We have the others that are occurring naturally, but others we don't know. For example, when we are doing blasting in the stony quarries, we have that dust that is given off. Some of that dust is at a level of what? At a nanoscale, but we don't know. So that's a man-made activity. And so our course is now focusing on how do we engineer these materials to solve our own problems in Africa. Okay? So because of those specific properties that we want, there's a gentleman that was trying to explain what he's doing, removing heavy metals. The question is, if you're removing heavy metals, is that product, can that product be applied in removing, okay, the planar kind of pharmaceuticals, the biplanar kind of pharmaceuticals? Because if I can remove a heavy metal, can I use it this way? That's why the dean was insisting. Everyone is doing almost the same thing. But can we find that distinct application, that distinct property, that we can say someone is removing pharmaceuticals and the other one is removing heavy metals because the scale at which these nanoparticles were produced for removal of heavy metals was this, and it was cheaper. But when we came to pharmaceuticals, because they are one of the emerging micropollutants globally, okay, we couldn't do that. And so what we focus on is what are the core characteristics of these materials. Okay, let's go on. Okay, move. These are the types of nanomaterials. For example, this is powder. You can see the nanotubes, and so you can see the dendrimers, and then you can see the restructured carbon dots, what we call the nano carbon dots. And then recently we've had an emerging practice of creating what we call composites. Okay? Composites help us reduce the cost of using a single expensive material. If you can dope, in materials we call it doping. If we can dope a material with something that is readily available, but then serves the same purpose okay, as though a pure material, which was expensive, was used. That is what we call actually reducing the cost. And I think Dr. Iga has done a lot around the composites, and I think he will be giving us more on this. Look at the carbon nanotubes, look at the powders. So some of these, especially for like drug delivery, you've heard of the nanobots in medicine, and where someone was demonstrating to us how you can target a particular tumor with a particular medicine without affecting the other organs in the body. That is what everyone would want to hear, so that then we do away with the chemotherapy, for example, where we can treat the cancer of the liver with a particular drug delivered to just that point without affecting the body. Those are the things that make us wake up early and try to research about what? Nanotechnology on a daily. So let's move. Yeah, some are carbon-based, others are metal-based, please. Faster, because others are metal-based, like metal sulfides and all that, but most others are carbon-based. As you can see, the titanium oxide, and some of these, like my colleague Dr. Chigos here, is so good at this, and he usually lectures me on what happens with these things, how he has managed to develop a very thin cell out of coffee husks. So some are carbon-based, like most of the work we are doing is carbon-based, but others are actually metal-based. Let's move faster. So you can see the dendrimers there. And so you can see, this is what I talked about. Sometimes we can have a nanomaterial in bulk. And so you build something from particles and you have this bulk, one phase or multi-phase, but then you can just do the surface. Okay? And so depending on what is easy for you and for that particular application, you can see, but then you can have particles where we can do maybe vaporized deposition on a surface, if they are particles. Okay? But there are some particles that are always suspended in liquids. Others are suspended in solids, and others are airborne, like the Sol-Gel method that our presenters were talking about, where you actually build a solid from what? You come up with a solid from a molecule. Okay, so these are the things we are looking at, and so the questions always come: why are you creating particles? Why aren't we just doing a block that can be used over and over again? Okay, and that's the same thing that comes. Why are we opting for powdered active carbon and not the opposite one, where we have actually real, not powdered form, but we have kind of particles? Okay. Granular, what we call granular activated carbon, so that we can reuse it over and over, unlike the powdered activated carbon that actually gets over contaminated and actually it loses value easily compared to the granular. Let's move. So there are different approaches. I hinted on this. We have the top down, where you can actually play around with the block, break it down, like you have your rice husks, break it down, what we call etching, then to the desired shape. Then the bottom up, you have the particles, and then you keep building on top of another. And then you have building materials atom by atom. Then you have the green synthesis. I think everyone likes anything green. Everyone says it's really a catchy thing. And I've always asked Dr. Zakatawa produce something for drugs. I think he was looking at drug resistance and I could curb bacteria. But I kept asking, are you sure that process was completely green? And so how do we then characterize the green process? What goes in there? Okay? Many of us think if we don't have burning, that is green. Okay? But those are the things we need to look at when we are writing some of our proposals to defend whether the process is green. So as you can see from atoms, then clusters, you have nanomaterials, but then you can etch a block, powder, and you also have nanomaterials. So the approach is actually, you can choose the approach depending on the base material you have. Let's move. So these are some of the nanoparticle synthesis. I'm not going to do more here because I'll be preempting. I think some of the content that Dr. Chigos will be actually giving us, like we can synthesize chemically, or we can do the physical synthesis where we do ablation, grinding, and all that. And then we can also do biological synthesis, which mainly is taken as what? The green the green process in many processes around here. So let's move. So these are some of the products we have in nanotechnology. We have building products, automotive products. You can see the oils. We have nano kind of adhesives that are being used in the construction industry. We have electronics and computers, especially microchips. Then we have cosmetics, food products, home and garden. Recently, I had a presentation from a professor from South Africa, University of Pretoria, where they have actually the waste from refining oil, the oil people, that waste from refining oil, they have actually produced a very good protein enhancement feed for children. And my thinking was, how do you get food from oil? You see? And it is now being patented. So at that level of research, those are the things we want to look at, because I couldn't believe till I saw actually a publication on it. And you mean you're feeding people something you've actually gotten from, moreover, not pure oil, but actually the residue. So people are doing a lot of work around this, and I think a lot is really going to happen. Let's move faster. So these are already I've talked about, where we have the transistors, the organic light emitting diodes in electronics, and then the nano transistors and nano diodes, how small they are. Some of us that have those old radios, we can open and look at those capacitors, okay, before we introduced even the ICs, the integrated circuits, how big these were, but now we have such. Let's move. In energy, I've talked about that. We are looking at lithium batteries, okay, improving lithium batteries, and also to do solar cells. This research is ongoing. Some of it is at the Department of Physics to actually integrate nanoparticles in solar cells, like the one we have here, the flexible solar cell. Let's move. So, they are lightweight, self-healing materials. These are some of the research that is ongoing at Makerere. Like we have nanotubes. Nanotubes have been applied mainly at the point of use in wastewater treatment. That's why when you go to those good hotels and then they tell you what is in the showers is actually what we call potable water. Water you can drink, but it's in the showers, okay? And so the question was, does this purification happen in a water tank? No, in that system, mainly they integrate what we call nanotubes at the point of use, okay? So we have the girls coming up. Let's move. And so the fluorine, and then the nanoalloys, and then those are ionic, but then also we have those that are pure metal nanoparticles. So these are different applications that you can use, and therefore the question is are your nanoparticles ionic or molecular? These are cases that come in, especially for the chemistry students. Are we producing ionic or molecular nanoparticles? And if they are molecular, are you sure they will be able to do this and this? Okay, those are the questions we should be having. Let's move. Let's move faster. So in medical and health, we've had research on producing, I think now the dean would be much interested in such, because he's so much interested in biomedical engineering applications. We've had research in actually producing contrast material for X-rays, and I think for MRI, yes, from nanoparticles, and someone at Mackay is using the iron ore to produce such contrast material. So some of these, like the research that I was hinting on, for example, if we have treatment and we attack a tumor or a particular cell at that level, I think that would be the best, okay, for cancer treatment. Let's move. In water treatment, we have a number of these, and I wouldn't want to dwell more here. Disinfection, absorption, some is by physisorption, nothing to do with the chemistry, but it's physically absorbed. So we have membranes created, okay? We have also photocatalysis, that is also actually affected by nanoparticles by just increasing the absorption of what? Rays, okay? So let's move. So other applications, we have vehicle catalytic converters, I talked of that. In paints, the weather guard we use, okay, the more advanced weather guard that we use for our paintings has actually additives at a nanoscale for it to be resistant to those adverse weather conditions. And then we have ultra high performance concrete, okay, that is being studied further to understand whether we can apply it on a large scale. Let's move. So this will be handled by Dr. Chigozi, because these are characterization techniques and will take us through that. Let's move. And then the fabrication, how do we fabricate this? Sometimes it's lithography, where it's just a beam, where we paint something on a surface using a beam, and then that surface, like you just draw art on a surface, but it's all nanoparticles all over. I talked of chemical vapor disposition or physical vapor, the soil synthesis that many of the students have been talking about, or we can even grow the crystals in the lab. Then there is this sketchy thing called epitaxy, where you actually build on top of another what? On top of another membrane, okay? And then etching is where we talked of producing powder from a block, and then masking, where you just attach kind of a surface on a particular item, and your specific purpose is to make sure it serves that purpose. Like in some of the latest aeroplanes, some of you that have been flying, you've seen some of those handles that have been coated with what? Nanoparticles. You've seen the latest Nike boots that cannot get dirty. You've seen them. Some of you that are into style, with updates from the Met Gala and all that. You've seen the latest Nike boots that cost millions. Now, these methods are all available, but then it depends on the equipment we have, okay? And then the purpose. It's not that we shall choose to maybe do molecular self-assembly like that, but we may not have that. There are things we need to, like the NMR, okay? Maybe we do not have such machines yet, but what we have, I'm sure we can do something, because most of these, some of the core equipment we have at Makerere, and also some are here. Let's move. I've really talked about this, okay? The advantages of nanotechnology, what it does. Some are industrial, some are medical. You know, you don't have to do university. I've seen people doing body tattooing using nanoparticles without actually feeling any pain, okay? That has also been good. And one time, Dr. Sekatawa produced nanoparticles that you couldn't handle by your bare hands. They will actually get into the pores of the skin. So some of those issues happen, and these are advantages, but also let's look at the disadvantages. There's all the advantages. We've talked of engineering, textile industries, and all that, but I want to look at the disadvantages also. Yeah, of course, people are losing jobs because of nanotechnology. But then also oil becomes worthless when we have EVs using what? Batteries that are less costly, because the main thing why EVs are not always taking off is the cost of the lithium ion battery, which also comes with an issue of disposal, okay? Then atomic weapons, more accessible and destructive, that is also bad, okay? Because some of the filthy bombers we have, those ones that actually some of the big countries use, they are just nano-coated, and so the radars cannot actually identify them, okay? Because of those nano-coatings. So research at Makerere and partners, we have vaccine delivery systems, drug delivery systems, imaging, nanosolar cells, energy storage, water purification. That's basically where I am. Diagnostic kits for respiratory infections like COVID-19. All these ones are being developed at Makerere. Let's move. And then we have the bioactive nanocoated masks with antimicrobial activity. Leave alone the 3 million UGX mask that someone bought during COVID. You remember that? It was all over papers. And so others we couldn't actually afford. But then we are trying to have something like that is bioactive. Then paramagnetic nanoparticles for extraction of nucleic acids. for PCR test kits. That's for the medical people. And then also we are trying to see how we can modify the cathode volumetrically wired metallic nanoparticles to enhance light trafficking efficiency of polymer solar cells and formulation of nanoparticles for the management of cancer. Let's move. A number of research is still ongoing. Some of this is not at the center, but we are collaborating as a university, different colleges, but we are collaborating. And so you've seen how people have come up with actually catalytic decomposition of selected plastic waste, where someone is actually trying to degrade plastic waste using nanotechnology. And also some of this is one of the, I've seen a publication on this, you can read about it, is by one of the PhD students based at the center, development of an improved bioactive gauze dressing using herb-loaded nanoparticles to facilitate wound healing. You just do like kind of a plaster and then it heals the wound, okay? A number of research interests that we can always ponder on and talk further. Let's move. Then, this is still research, but I'll mention this. Well, design and fabrication of chemical sensor based on molecular imprinted conducting polymers, composite nanomaterials for aflatoxins monitoring in consumer products. This one has been actually, people have got buy-in from the Minister of Agriculture. Remember the case that happened when actually our maize was rejected in South Sudan because of aflatoxins, okay? And so many of our farmers use actually chemicals in that maize to actually keep away the pests. So someone who is looking at aphids, right? You would actually, this would be good literature review on this study, how they are doing this for aflatoxins monitoring in consumable products, and how are they doing this monitoring? Nano water filters for provision of safe drinking water, especially at the point of use, okay? Now, this other one, I've always failed to pronounce this. I think it's for the medical people with all the big words. Dodonavisco, I don't know. I don't want really to do bad service here. Let's move. So these are the facilities available at Makerere. You put the pictures also, okay? So the ACM, XRD, ICP, FTIR, and others available at Makerere. Of course, the usual ones like the furnaces, the extractors, the filters are always there, okay? And we have good collaboration with some of other research institutions where we have like SCPM, high performance liquid chromatography with other institutions, okay? We move, okay? So in future, we want to really leverage this nanotechnology and reach to close the $3 trillion US within 10 years by leveraging nanotechnology in all these fields that we've been talking about. And with that, please allow me to stop here. Thank you.
Thank you so much, Dr. Ronald. I just have a few announcements. Those going to present tomorrow, kindly go for lunch, but before you leave, our team will be there to receive the presentations. So do not leave before submitting them to avoid inconveniences. Anyone who wants their photo of today, I'm not charging you. Follow us on Twitter, Facebook, Instagram, and LinkedIn. Mbarara UST on Twitter. Mbarara UST on Twitter. Mbarara UST on Twitter. Mbarara University of Science and Technology on Facebook, Instagram. Smile, what is the LinkedIn? Still the same. LinkedIn, just write the name and find us there. Then amidst us, ladies and gentlemen, I do welcome and recognize the university auditor, Mr. Mutebi. Thank you for coming. It means a lot to us. This is audit and accountability. Thank you for being with us. Ladies and gentlemen, now you're Ugandans like me. Go and rest. Tomorrow is very long. After lunch, go back to your hotel rooms, relax, and then tomorrow is longer than what we thought. This marks the end of today. And tomorrow we're going to be in the studio. We're in the boardroom today because we thought the people presenting online would be here, but we've gotten the same facility in the studio. So we'll just walk straight. We'll have the ushers lead you tomorrow. And still, before you leave, kindly receive the outfit you're going to wear tomorrow so that we don't stay must, no. You're Mark, actually. Mark must. Hey, Mark must. Hey, we are shouting at each other. So tomorrow we are the same. So the visitors don't differentiate who is who. When they're throwing their money, they throw it anywhere. Deal or no deal? Bon appetit. Do we have a pastor here to pray for our food or Hajat? I knew it. That outfit is not for. Amen.
Okay, let's humble ourselves for a word of prayer. Heavenly Father, we thank you for this day. We thank you for our lives. We thank you for the organizers. We thank you for Mbarara University. We thank you for whoever has made this successful. Heavenly Father, as we break off, may we have the best. May we have protection. May we actually do progress in whatever we are working on. And as we usher ourselves into lunch, whatever we are going to eat, we actually bless that we are still alive and we shall actually be here tomorrow by your grace. If we pray and thank you in Jesus' name, amen.
Thank you so much, Pastor. The amen was not strong. In Jesus' name, in his name. We're covering our sisters. The MUST team, kindly stay behind. This is again Mbarara University of Science and Technology. We're going to do post-mortem of day 1. So our guests, please go for lunch. MUST team, stay behind for post-mortem. And we know the cause of death. Thank you. Lunch is just in the next room there. Please meet and greet and take the necessary contacts. I would request Martin and your team, my ushers, yes, to lead the people to the lunchroom.
Oh, I've remembered her face. I'm trying to get to her face.
The MUST team, please pull forward this side. Pull forward, MUST team. We're going to have a meeting here. Dr. Jones, please lead the guests for lunch. My ushers, Lillian and Tim, kindly take the people. The MOOC team, kindly go for lunch. And our petroleum people, please go for lunch. Yes. Sagara. Mami yali akuyita. Babiri, go for lunch. Hadija, bust. Okay, Mr. Sagala, our meeting is this side with the MUST team. Who's in charge of now the MOOC people hear our secrets. Who's in charge of the t-shirts? These guys have to go with their t-shirts. Martin? Can you call me the person in charge of t-shirts? Okay, lecturers, I think you go. Let me stay with this.